Maybe too much.
It's always there.
I was kind of thinking it can be used as some kind of
Okay.
Mickiewicz.
Okay, so we can start.
Okay, so hello everyone. Good afternoon. Today we have a guest, Bruno Šlaus. Bruno is a postdoc in Poznań at the Mickiewicz University, working with a group of Michał Michałowski. He is originally from Croatia, from Zagreb, where he actually graduated and did his PhD there. And he's right now working on the project about AGNs and some sub-millimetre observations. And Bruno speaks Polish, actually. So, but the seminar.
But I will speak Polish.
Yeah. So he learns quite a lot. But the seminar will be in English. So the floor is yours, and we are happy you came and accepted our invitation.
Thank you very much, and thank you for inviting me. So yes, as you heard, my name is Bruno, and I'm going to talk about AGN in sub-millimetre galaxies. Sorry, just do you have something to change the slides, or can I?
Yeah, I have to press that.
I can do it like this. It's okay.
No, it works mostly, so we have to check it. Their batteries are working, but maybe this will work. This will work. So, oh no, Marius.
Oh, I have no more.
No, let's maybe just.
Okay, so without that, oh, sorry. Yeah.
Okay.
If you press play.
Where's the place? So it used to be a 5 for me. Okay. This one. No, unfortunately, sorry, it's not working yet.
No.
Doesn't work.
We can also scroll.
Okay, should be fine.
Weird.
Yeah, it's very weird.
I never saw this, to be honest. No.
Strange, but slow.
Let me then scroll rather.
Okay.
Sorry for this.
No, not a problem. Oh, now it seems to be working. Okay. Okay, good. So once again, sorry. So Bruno and I'll talk about AGN contribution of scuba detected sub-millimetre galaxies. So the main topic is sub-millimetre sources, and we will try to talk about and try to estimate the AGN contribution within the sample of sub-millimetre galaxies. Now you must keep in mind that this is still very much a work in progress. So in other words, I just started working on this. So I will tell you what we have accomplished up to now, and what we then hope. And also I will give you a brief review of sub-millimetre galaxies in general and the AGNs within these sub-millimetre galaxies. So for students, I think this should be interesting. So let's talk briefly about sub-millimetre galaxies in general. So sub-millimetre galaxies, well, obviously these are galaxies that are detected in the sub-millimetre part of the spectrum, and that is where the name comes from. Now, physically speaking, these are dusty star-forming galaxies. So these are galaxies that have a lot of dust and a lot of star formation, and then they emit, but because they're usually at higher redshift, the emission gets shifted to the sub-millimeter part of the spectrum. Okay, and there are a few things that are very good about sub-millimeter galaxies, and a few things that are interesting for people to do with sub-millimeter galaxies. Now, first, what is like a very positive thing about sub-millimeter galaxies? Well, this is the very negative K correction. So, and when we say very negative K correction, we mean, in other words, very good for us K correction, because K correction, very simply put, because of the spectrum of a source, it can emit stronger at some frequencies and weaker at other frequencies. And then when you shift it due to redshift, you can shift it to the part of the SED where it emits stronger, and you can shift it to the part of the SED that emits weaker. And for sub-millimeter galaxies, it gets constantly shifted to the part of the spectrum where it emits stronger. So in other words, as the galaxy goes to higher and higher redshifts, as we observe sources with higher and higher redshifts, the K correction is always very negative. And you can see this also on the plot on the right. Let's take the purple line, which is 850 micrometers. This will be the frequency of our scuba detections. As you can see, this is on the y-axis, okay, it's a bit too small. On the y-axis is the flux, which you observe, and on the x-axis is the redshift. And you can see that all the way from redshift 1 to 8, 9, maybe even 10, the flux of the observed galaxy stays constant. Or in other words, it's equally easy to observe a galaxy at redshift 1 and at redshift 8, which is a very good thing, because you can see very high ratio galaxies. Now, another thing which is interesting about sub-millimeter galaxies is the fact that they exhibit a lot of star formation, more than it is usually predicted from the models. So this is a very strong constraint on all kinds of galaxy evolution models. Also, they're way more numerous than the local analogy of ULIRGs, which is ultra-luminous infrared galaxies. Now, ULIRGs is mentioned here, and that is very nice, because maybe we can try to explain a bit about sub-millimeter galaxies by talking about ULIRGs, which are readily available because they're at the local universe, right? Of course, this analogy is not complete, because things that happen in the local universe don't necessarily happen in the same way at very high redshifts, but maybe we can learn something about sub-millimeter sources when we talk about ULIRGs. So these ULIRGs, they're ultra-luminous or just luminous, depending on the luminosity, infrared galaxies, and they exhibit a lot of star formation. They're a special type of objects. And one way to explain their origin and evolution is presented here. Is a physical picture of mergers. So basically, this is a standard thing in galaxy evolution, how you explain how galaxy goes from a disk-like galaxy to the elliptical galaxy, where the disk-like galaxy creates stars and it's bluish, and the elliptical galaxy is dead and red, as they said. People like to call them red and dead galaxies. Okay. So this is the main, or the most accepted paradigm now. So we have disk galaxies, then they merge. This merger causes an inflow of gas, which then causes star formation. Now, this inflow of gas also ignites the AGN, which is the central black hole of the galaxy. And then you can have a lot of infrared emission from the stars and even the AGN, which heats all the gas and emits in the infrared parts of the spectrum. Okay, so this is one way to understand it. And for us, or for this work, the important part is that maybe there's also AGN flaring here. Because if we have a merger, then it's kind of expected that not only star formation will be ignited, but also an AGN, which is then interesting for us, because the title of the topic is the AGN contribution to the sub-millimeter galaxies. Of course, this is ULIRG, not really a yet high redshift sub-millimeter galaxies, but okay, it gives us an idea, right? Another thing is also the distribution with redshift of sub-millimeter galaxies. This is not my work, this is earlier work. And as you can see, this histogram, you can concentrate on the red lines. These are just three different surveys. But if you concentrate on the red line, you can see from this bigger survey that basically these are sub-millimeter galaxies, and they're distributed according to the redshift. And you can see that these peaks are at around 2. So a redshift of about 2. Which is the same place where AGN also peak. there's another possible connection here that we can explain, that we can expect maybe to have AGN within our sub-millimeter sample. Okay, and a lot of different surveys have already tried to estimate this, and this is a table. Okay, it may be a bit dry to just give a lot of references like this, but I think we need a few minutes to go through them because it's pretty interesting. So these are all of the surveys that I was able to find. I'm not sure if these are like 100% of them, but I think there's quite a lot of them, you know, going through the references. These are all surveys that try to estimate the fraction of AGN within the sub-millimeter sample. So they were basically interested in the same thing that we are trying to do. So first, it all started with this guy called Alexander in 2005. And he had a sample. So this is on the last column is the number of sub-millimeter galaxies used in the survey. And the AGN fraction is AGN and then the percentage mark. So, thanks. Yeah, so this is the fraction of AGN, and this is the number of sources of the complete sample. Okay, so as you can see, Alexander had only 20 sub-millimeter galaxies, and 15 of them, or 75%, he managed to classify as AGN. It should be said that all of these surveys that are denoted as X-ray did the same thing, and that is they had a sub-millimeter sample, which they matched with X-ray, and then depending on the X-ray emission, they decided whether this X-ray is too strong to be just star formation, so they decided, okay, this is obvious an AGN, right? And this is what Alexander did, and he said 75%. Later on, it's the same person in the same year. He had another paper in Nature where he basically said, okay, this is maybe a bit too optimistic. The thing is, his sample was not really random, you know, this time he decided to check the so-called interesting sources and so on. So he had some theoretical reasoning to lower this percentage to about 38%, right? So this is, I would take this as to be the first good estimate of AGN fraction. Then after him, we have Lard et al. Who put it to 20 to 29 on 35 sub-millimeter sources. Then we have okay, Gorgon to Lopos et al. 2011, who put it less than 26. Then Johnson, interestingly, put it at 14, which is pretty low on a pretty big sample. And now the next important one is probably the Wang one. And this one is important because this is the first time that for this they used interferometers. So in other words, all of these surveys before, they had single dish observations. And pretty soon you will see that there's a big difference between single dish observations and the interferometers. And Wang et al., he used ALMA, which is an interferometer, which means that his sample is simply better, it has better resolution. So, and he then gave an estimate of 17. Okay, then we have Ueda et al. Okay, this estimate is a bit off because he used only high luminosity sources. And then the last one is more than 16 on a very large sample of 260 galaxies. So as you can see, they all kind of go around 20 to 30, maybe 10 to 30, I would say. So we have some kind of a rough estimate of how much AGN we expect, although it should be said that these are X-ray detected AGN. The way we classify AGN, of course, means the kind of AGN that we get in a way, right? So, okay, some people try to use the infrared emission also, but they usually put constraints on the luminosity and not on the numbers. And then we have the staff and all who did both X-ray and infrared and set 8 to 28. And the last one is probably also important for this talk because they use radio method of AGN selection. Or in other words, they said that they will classify the AGN by radio axis. So in other words, if there's more radio than you expect from the star formation, then this radio emission must come from AGN. And this is an elegant way that people have been classifying AGN for quite a long time. 13% here and this huge number of sources is also a bit misleading because they don't have only sub-millimeter sources, they have a bunch of different frequencies, but they do use radio access. That is why I put it here because it's interesting for us. So, okay, so this is the main like current state of the art of the field, right? And now we're trying to do similar things here. Another thing, let's go back to the Uematsu paper, which is also interesting for us. They also looked at their AGN sample and tried to see how many mergers there are in this AGN sample. And they found that they have 47% mergers for AGN, and only 25% mergers for the non-AGN sample. So in other words, it's kind of expected that AGN are correlated with mergers, right? Which would kind of also bring us back to the first or the second thing I showed, where the AGN emission was basically a consequence of a merger. It should be said this is not the only explanation, but this is what the observations show. So there's more mergers for AGN than there are for non-AGN. So we need to keep this in mind. Oh, wrong side. Okay, so let's talk about briefly about sub-millimetre surveys in general. There's a lot of them, and this is basically all the lines. The vertical lines are the different surveys superimposed on a typical SUV galaxy. And we will use SCUBA 2 data. So this is here it is. And this is observed at 850 microns. Okay. And now the thing is, when you have this kind of observation, that's okay, but this only if you have only sub-millimetre observations, then you're missing a lot of information. First, you're missing a lot of emission from all kinds of different frequencies, but also you're missing redshifts. So usually you do want to cross-correlate. And the cross-correlation is much more complicated than one would usually assume. And the reason for this is that single dish observation, and SCUBA that we use is a single dish telescope. They have horrible resolution. So we're talking about, this is the PSF of our SCUBA 2 telescope or camera. And basically the PSF is 14, let's say 15 arc seconds, right? So the resolution at full width half maximum is 15 arc seconds, which is really not good, right? And now I also plotted, these are my catalogs, so this is basically the data that we're using. I plotted this as a gray circle, and then I plotted also my optical catalogs that we're using, and green the radio catalog. So as you can see from here, if you try to match sub-millimetre sources directly to optical sources, you will not have a good time, because within the beam you have around 20-ish optical sources, right? So what people do is they usually match it to radio. And as you can see from the green dots, which are radio, this has a larger chance of success. So this basically gets us to the main idea of most of these surveys do sub-millimetre stuff. First you match to radio, and then you match to optical once you have the radio identifications. And this is basically the way most people do it. Another thing is here we have also the far infrared to radio correlation. So it's kind of expected that there's a line connecting the infrared and radio emission, which also gives us a reason why we want to go to radio first and then maybe to optical if we want optical. Now also a few words about the details of this, because this is basically the thing that I have been doing for the last month or so, trying to cross-correlate the sub-millimetre sources as well as, you know, as good as possible to the radio detections. And one very common method which people use is the Poissonian probability method. And it is a very simple method. You can assume that the red dot is the sub-millimetre source, and then you say, okay, the green source is the radio identification, and then you calculate what is the chance of this match being purely random. And the way to do it, of course, is to use the Poissonian equation. So in other words, by using this equation, we can say, okay, we have so and so such and such percentage of this match being completely random. For instance, if we have like a 2% of the chance of the match being random, that means that there's a 98% chance that it is not random, or in other words, that it is a real identification. So, and this is what we do, and this works only because the radio is not dense, like there's not a lot of sources. If we had optical sources here, we will get very, very large percentages for each possible radius, and this would not obviously work. Okay, so of course, this is not the only way. I also list a few other methods here by different authors. For instance, our method, or the method that we're using, it basically attributes to each different match a certain value. So we say, okay, there's 2% chance that this match to this radio source or this sub-millimeter source is random. But these people for Boris et al., they try to estimate it, for instance, for the complete sample. For us, it is not so interesting because we would like to have an estimate for each individual match. Also, some people say that the separation, like the maximum radio that is allowed, the maximum radius that is allowed between the radio and the sub-millimeter should depend on the signal to noise, which at first would make a bit sense, because maybe if there's higher signal to noise of the sub-millimeter sources, then you can expect maybe that their position is better determined and so on. But this is actually far more controversial than this, and there were some papers that tried to estimate whether or not it really depends on the signal to noise of the sub-millimeter sample, and actually it's non-conclusive really. So some papers say yes, some papers say no. So for our purposes, we decided not to do it then because we can't really know. And then there's some very complicated methods, like for instance, Chen et al. Used some colors. Of course, colors, that means they also had the optical. So they went to radio and then to optical. And then with these opticals, they said, okay, probably these are red galaxies because they emit a lot of star formation, which is dust shrouded. So there's some kind of cuts in colors, and there are 3 colors here. That's why it's called TC. I guess it's 3 colors or so on. But this is, again, too complicated for minimal advantages, and what is even more complicated is, of course, the machine learning, which by admission of Liu et al., I think about 5% of increase in the number of good matches would occur here. So we decided against those two. So we're basically using the Poisson method here. Now a few words about our data sets. It comes from SCUBA 2. So this is an improved SCUBA camera on the James Clark Maxwell telescope. We have about 2,200 sources. So this is a nice sample. Of course, this is only sub-millimeter. When we match it, it will go down because not every sub-millimeter source will have a radio and optical counterpart. But still, it's a nice size for sample. Unfortunately, also it's single dish and not interferometer, which means that, well, the resolution is not great. But we must live with this. This is the name of the survey. It's called Cosmology Legacy Survey. Basically, we use this one, the UDS, and then we use the COSMOS. But COSMOS will have 4 pointings. Actually, it does have already 4 pointings, but it did not have in 2017. So this picture is maybe misleading. But we will use the 4 pointings of COSMOS and the UDS field because there's a lot of different frequencies here, and this should give us enough of a sample. Okay, so here are all the surveys that we use. We use the SCUBA at the sub-millimeter. We use MIGHTY at the radio. We use then 8 and 24. 8 and 24 here, basically, they are also like radio. They're also not dense. So we'll match SCUBA to radio, and then we will match this to optical. But we will also try SCUBA to 8 and then to optical, and SCUBA to 24 and then to optical to see what we get here. But and each time we will match it, of course, as I said, with Poissonian probabilities attached. Of course, it would be the easiest to do it with radio because 24 and 8 are more dense, they're more numerous sources. But anyway, we try to do all of it. And the thing that I also did was check the astrometry. So as you probably can imagine, there's always a possibility of a little shift between the radio and the optical, or between the SCUBA and the radio. And this shift can be systematic due to a variety of things within the calibration and observation, right? So usually when people, I come from radio astronomy, so I matched a lot of radio catalog to optical catalog, but usually people first always check the astrometry because it can be problematic. So we did the same thing, but this time also with SCUBA sources. And this is basically, so all the surveys compared to radio. Usually people assume that radio is the best one because it's not influenced by atmosphere. And it's usually the best when it comes to astrometry. So we check this, and we have some offsets which are presented here. So this is the mean and the 3 sigma, but on the mean. So this is not the 3 sigma of the sample, but the 3 sigma of the sample divided by the square root of n. So the positional uncertainty of the peak. And then we decided to shift all of the catalogs relatively to the radio one, which then had an effect on the radii between the separations between each of those. And basically, unfortunately, this is now where it stops for us, because I finished this cross correlation. I hopefully successfully. I will have to check it again, but no further physics has been performed because well, I had no time simply said. So I will tell you about what we plan to do from now on and what we are afraid that can be a problem. Here, first, if you are interested in the preliminary result, this is the radio histogram and then the scuba detections, and then this is the ratio of those detections. So this is the number, the ratio of detected scuba within radio as a function of flux. Sorry, this is very small here. I should have made it larger. So on the x-axis there's a flux, and here is a ratio. So radio flux and ratio of identifications. But unless somebody sees something here, personally, I don't see anything really here that worth reporting. Yes. And now let's talk about what we plan to do and what we're afraid of happening. First thing that we plan to do before we continue is to look at this multi-component sources. So in other words, in radio, you can always have these kind of situations where you basically have a core of the galaxy and then 2 jets, right? And then if you kind of cross-correlate blindly, and let's say you have something here, and something here, and then if you just blindly cross-correlate, you can have 3 different sources, which are physically not 3 different sources, right? This is very problematic for optical, which is very dense, but I want to check it also for scuba just to be 100% sure what we see here. Probably it will be a mess because of the resolution of the scuba, but okay, this is something we need to take into account, right? Because also, right, the catalog, the radio catalog, this will be 1 source, 2 source, 3 source, and this can be problematic because in the end you will have to then sum all the fluxes, right? Because you will otherwise have a wrong radio flux. So this is something that we need to do and we will do. This shouldn't be too much of a problem. The second thing is probably more dangerous, and that gives us it goes back to the resolution of the scuba sources. And this is actually a very interesting study by Hodge et al. Basically, she had Laboca sources. These are single dish, so the same as our scuba, and she had the ALMA detection of those same sources, right? And what she found out that a lot of the sources that scuba or Laboca would deem a single source are actually 2 or 3, sometimes even sub-millimetre galaxies that, because of the resolution, get smeared out. This is called the confusion limit. Because well, the resolution is so bad that you cannot really say whether this is 1 very strong source or maybe 2 sources, right? And as you can see, also she plotted flux and then the number of multiples of black and gray. It depends on some details, but both black and gray are multiples. And what you can see also, which is especially dangerous, that for very high fluxes in sub-millimeter, you have only multiples, which actually makes much sense because it's not really a very strong source. It's actually 2 normalish sources that are blended together, right? So before we continue with anything, we need to address this because this can be dangerous, not only because of some of them being blended, but because this percentage of them being blended can depend on flux, right? So we can have some kind of a systematic bias depending on flux, which is then again not something you want to have. So we'll try to think how to, as well as we can, estimate this and maybe even use some ALMA data for R and try to estimate how much blended sources we expect. The worst case scenario, we can simply put constraints or error bars on all our results, taking into account earlier studies than this. right? But it should be taken into account. And then once we finally finish with this, the last step that we want to do is get this AGN classification. And probably it will be done by radio access because we have radio data and we have sub-millimetre data. And then from the optical catalog, we have redshifts, which means that we will have radio luminosity, we will have sub-millimetre luminosity, and then we can, usually you expect them to be on the line for star-forming galaxies. This is called the infrared radio population. But if there's AGN, as you can see from some earlier work here, then they go and deviate from this line. And you can put threshold then and say, okay, everything that deviates this much was probably an AGN. Okay, of course, if you have radio flux, it's relatively easy to get radio luminosity because radio spectrum is just a power law synchrotron. Now, for sub-millimeters, we're not 100% sure. Some people SED fits, but probably we're also lucky that we're in the regime where it's also a power law. If you remember the SED from before, we just need to estimate it one, like to be sure that it's so. But I think it is. So we can indeed, I mean, the worst case scenario is that we have to SED fit, but I don't think we will need to SED fit. We will just be able to find the sub-millimeter luminosity reasonably easy. And then hopefully we can get our own estimate of the percentage of AGN classification. And then later on, if we want, we can also maybe do some more physical things like, I don't know, there's a lot of ideas floating around here. If you have any of them yourselves, please share. But the main point and the main goal that we have now is to have our own estimate on the new SCUBA 2 data of the fraction of AGN within the sample. That will be what we want, because this is interesting both for the people who work on AGN in sub-millimeter galaxies, but also for the people who work on sub-millimeter galaxies and star formation and the model of star formation, because for those people, the AGN is a contribution that they don't want, so they have to eliminate it, right? So for both kinds of these surveys, so the galaxy evolution of star formation and of AGN, it is an important result. And now with new data, again, we will give our own estimate of the AGN fraction, hopefully with radio access classification, which also makes it interesting because if you remember, most of those were X-ray detected, right? I think this should be just a second. Yeah, there's a lot of references here. If you want, you can read all of them as some kind of a review paper or something. So I leave it here.
Thank you. Thank you, Bruno. So how big is the sample?
2,200 sources, only some millimeters. Once you match them, I must admit I forgot, but it drops.
But is that 1,000 or something like that?
Yes.
It still ends up, and then, I mean, the idea is to check how many of them are, if you plot them at this final plot, how many of them is above, which means that there are AGN. So if the percentage is 17 or 75, right?
Right.
So, okay, because that was, thank you.
I mean, we accept between 10, we expect between 10 and 30 from all the other.
Surveys, yeah.
Yeah, I wouldn't expect that 75%, that would be great, right? But some estimate between 10 and 30, I would expect should be.
Okay. Cool. Any questions or comments?
Yeah.
Mateusz?
I have a question. On the previous slide, you showed the correlation between the this line, the line, violet line. So you assume that they supposed to lay on the line based on what?
Well, because there are reasons to believe that there's no AGN contribution. There's this relation between this. I think just a second. Yeah, okay, between infrared and radio, let's say. I don't really remember exactly this paper, but for us it will be radio versus infrared, right? And then for star forming, it should be aligned. This is an experimentally verified thing. It is really aligned, right? But if something then deviates from this line, that means that there's a lot of radio emission coming from somewhere, which is not star formation probably, right? So it must be AGN. And this is the main idea. Because radio will penetrate through dust and stuff, so the axis of it should be clearly visible, and it will be a signature of the AGN. in this paper, this is not my paper, so maybe it's not best to talk about it too deeply, but you can read it yourself. But these are classified by different means into ULIRG, ULIRGs. So ULIRG and ULIRGs, these are all classification of different types of AGN. It becomes very complicated. There's a gazillion different nomenclature for all kinds of AGN, but both of them are AGN. So basically, both the ULIRGs, so the purplish triangles and the green triangles, they deviate from the lines, as you can see. Of course, this another thing which must be said. This will only be radio loud AGN, or in other words, the AGN that have an excess of radio emission. These are not all AGN. So the way you classify AGN is the final product you get. It's not the same whether you use X-ray or radio excess or whatever. You have to be careful with the classification. So basically, in our paper, we'll always have to write. We'll not write the percentage of all AGN. We will have to say the percentage of radio excess AGN.
So maybe the differences that you show on the first or one of the first slides between the different papers, it's not connected to that.
Let's go back here. Let's go back. Yeah, let's go back here because they were given. Sorry, it goes long. I also gave the method basically on the left. So I can see most of them are X-ray. So they use X-ray. Most of them are X-ray. And some of them use infrared. Some of them use X-ray plus infrared. And then only one, as far as I know, this very recent one, did it with radio access. And basically, they didn't really do this like the main result. They were interested in the luminosity function of radio access sources. So they had like a mixture of sub-millimetre, some other infrared detections. And then they did the radio access to have a sample of AGN. So this is not really exactly the same question as we have, but the methodology is similar, right? So we have one paper that does the radio, and they're basically doing it on a different sample with different aims, right? As far as I know, right? So this is why also it's kind of interesting what we're doing, right? Because this is, from that perspective, is also relatively new, right? We don't use the X-ray. Which, of course, it all depends also on the thing how good our radio data is, because it depends on the depth of the radio data, stuff like that. But this is all something that we can think about also later, maybe via upper limits and lower limits. For instance, even for stuff in sub-millimetre that doesn't have a radio detection, it can be interesting to see the upper limit, right? Because usually I expect radio to be the problem with depth here, because like I said, sub-millimetre galaxies are really deep. That is their main selling point. Yeah, because they go also with all these kind of work, right? But we can always also play with upper lower limit. Right now, of course, I can't say much more than this because this hasn't been performed yet. But maybe it will be something to do.
More questions, comments? So I have also one question about this last part. So you have to go back and go further.
Yeah.
There's this unclassified class or something like this. The red one that is like a vertical almost. Why is it so? I mean,
From that paper, I must admit I don't remember, to be honest. We will
because
have to
it's
look.
quite
Yeah, they all
suspicious.
yeah, they all these are, but they have like little arrows. It's not visible here, so these are basically like upper limits. So it's somewhere on the left. Yeah. Yeah, it's not visible. There's arrows pointing that direction. So basically, it's somewhere.
Okay.
And I personally think this is kind of useless to plot, to be honest, because it's.
So what's your guess about the number?
That's a good question. I don't know. I think between 10 and 30 probably. I don't expect anything special here, but also we'll kind of look maybe later on if we can maybe correlate it to some physical stuff, maybe with mergers or densities and stuff like that. Maybe there's some interesting physics being performed here. I can't really say much here yet because I don't know, but there's a lot of brainstorming going on now. I mean, I have codes for densities prepared for some other work, so it's not really hard to estimate the densities of these sources, like, I mean, spatial densities, right?
But you have all the observations. So you
Yeah.
have to- yeah.
Yeah, actually,
surveys.
I need to just look maybe at, I showed here for COSMOS. For UDS, I need to talk to Michał about the 8.0 sources yet. There's something fishy about this catalog, but
Okay,
we will-
but
we
the
will-
data is.
yeah, it's publicly available. It's this is all of these. I mean, Scuba 2 is also publicly available. So all of these actual catalogs are now publicly available. We are kind of we're not kind of doing something on a new unavailable catalog here. So in other words, the strength of the work we hope will be in the idea of methodology here. The catalogs are better.
Okay. Don't see any more questions, comments? Anyone on Zoom? Let me check. Maybe you can help me.
I will try.
I didn't want to disturb your presentation, but I think there were some people, but I don't see any questions. So yeah, if not, so let's thank the speaker again. Thank you. And next week we will have a guest from TAMP talking about some galactic archaeology. So see you then. Thank you. And don't forget to fill your names in the. Thank you. Nice. Actually, the point that Mateusz had that.